Well, a warm welcome, everybody. Thank you for being here. Get yourself ready with maybe some graph paper. A notebook is fine as well. Pencil or pen, whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we're going to take a look at some problems from a previous video covering piecewise functions. We just talked about how to evaluate piecewise functions, so if you haven't checked that out, please do go give it a look-see. And in that video, I did encourage you to try to graph some of these. If you wanted to just look at them on Desmos, that's sort of bare minimum. If you were willing to take the challenge and try to graph these, maybe it wasn't too much of a challenge, just depends on what level you're at. But if you were willing to take that challenge, you can check your answers here. And if you're just ever so curious what these graphs look like and you want to see, keep watching this video and we'll get into it. If you do like the videos, please give it a like actually a like on the platform. Subscribe to the channel or send this video to somebody that you think could use some help. All right, let's get started. So what I have here are the same examples from yesterday, and I still have the same notes, which is where we evaluated this piecewise function at some various different x values. And I'll just recap that. Depending on which x values you're trying to plug in, this section here, the domain section of the piecewise function, is going to inform you, is going to guide you to using the correct piece in order to evaluate the function. So that's just a reminder. And we're going to focus on this domain section here because rather than a grid, a normal XY axis, you'll notice I just have a number line right here. And the reason for that is simple. The breaking point, I'm going to call this a potential breaking point, is determined at the x values where these domains sort of trade off. All right, so we have a potential breaking point at x equals 0, for example. So what does that look like? Well, I haven't drawn the y-axis yet for two reasons. One reason is because I just want to focus on the x values, the domain. But another reason is that this potential breaking point at x equals 0, that overlaps with the y-axis. So if I already had the y-axis drawn here, you wouldn't really be able to see what I'm about to do. So here is 0 on the x-axis, and we're going to have this potential breaking point, which can be represented by like just a dotted line. It doesn't really mean an asymptote in this case. I know that a lot of times we use this to mean, oh, there's some kind of asymptotic boundary for the function, but we're just thinking about this as the breaking point of the two pieces. And then I can go ahead and draw the y-axis sort of overlapping it. But I want you to keep focus on this x equals 0 sort of boundary line because that's where the two graphs are going to switch off, the two pieces. So let's get graphing this. This says that we're going to graph 4x plus 3, which is just a line with a slope of 3. We're going to graph that whenever x is less than 0 or equals to 0. Now, if we wanted to sketch the graph, we would just sort of draw a line with a slope of 4, and it would go through 1, 2, 3. It would go through this point, that's the y-intercept, and do something like that and go forever. But because we're looking at a piecewise function which breaks off or sort of stops at x equals 0, we only want this portion of the line. And the kind of, maybe I should label this a little bit better. This will be -1, and this would be -1. So we have another point here, and now you can draw the segment, or the ray, it's technically a ray, if you're a math nerd like me, that goes through that point. So I just wanted another point so that I can get an estimate. If you were graphing this on paper, definitely use a ruler. It's simple to get a ruler. anything straight, really, and draw your straight lines there. So as I said, this line theoretically would continue with a slope of 4 going upwards like that. But we're cutting it off at x is 0. And notice that there's a solid dot here. Let's notice that. There's a solid dot here because the first piece, you'll notice, includes 0 in the domain. So it's less than or equals to 0. Whereas the second piece that we're going to graph, this is also a line with a y-intercept of 1 and a slope of -1. So it would have a point here, and then it would continue down 1 over 1. So this line would look something like that. However, you can see they're overlapping, and this would violate the rules for a function. So that's why this domain comes in handy. The domain restriction for this piece says x must be greater, strictly greater than 0. It can't even be equal to 0. So you know what I got to do is I even have to eliminate that little dot. It's not going to be a dot there anymore. It's going to be an open circle because we're getting up to that spot but not including it. So the best way to indicate that is just with a little open circle. And then we can continue this. It's not really a ray because it doesn't come from a point, but I think you get the idea. We can continue this portion of the line going to the right when x is greater than 0. Okay, and I didn't have to label things like crazy. If you have grid paper, I encourage you to get a notebook with some graph paper, like I don't know, they sell those, not just lined paper, but they also sell some graph paper notebooks. I encourage that for all graphs. Or if you have a ruler and you have the time and you're patient enough, you can draw out the grids, but it takes a little bit of time to do that. Okay, so this is what the function looks like. Let us remind ourselves that these piecewise functions, as the name suggests, are functions, meaning they pass the vertical line test. They do not have any repeated y values for a given x value. I can draw a vertical line anywhere, and it will cross at most once, so it satisfies a function in that sense. Okay, let's move on to another example. Example 2. This is example 2 from yesterday. Now we have a similar domain restriction here. This is the potential breaking point. So on my number line, I'm going to have 0. And then I'm going to draw my vertical breaking, my sort of line of, what should we call it? It's not a line of reflection, really. It's not like you're looking into the water and seeing a reflection, but just sort of like the cutoff, the trade-off spot, you know? It's like if you were running a relay race, or when they run a relay race in the Olympics and they hand off the baton. It's almost like that. It's a nice clean handoff when they match up together, and it's not so nice of a matchup when they don't hand it off exactly. But I think you get what I mean. The analogy breaks down a little bit. So there's the trade-off x value, which is at 0. And let's think about what these would look like. So we have x squared minus 3. In fact, I didn't use any of the specific points. I probably should have used some of these points. I did use a couple of these points. Like here's 2, -1. I didn't quite use -2, -5, but you can see that would just be down there, right? -5, something like that. Okay, so you can use the points from the previous video as, to your advantage. When we plugged in -2, which piece were we using? We were using first piece, and when we plugged in x equals 0, and when we plugged in x equals 5, we're using the second piece. That's pretty much how that works. Okay, so let's get this on the grid. X squared minus 3. What would that normally look like? You should recognize that as a quadratic, which means its graph is a parabola. It's technically incorrect to say that x squared minus 3 is a parabola. It's a quadratic expression whose graph is the shape of a parabola, but, that's just being really, really technical. So we see that it's just a standard parabola, which is shifted down 3 units, which means if we go down by 3, -3 right there, we should have a spot here. But is it a solid dot? Let's look back oh no, it is not a solid dot because this domain restriction for the first piece does not include 0. So we're going to take away that bold dot and we're just going to make it an open circle. Now here's where, if you're not too familiar with the behavior of x squared or a quadratic function, it could get a little bit tricky. So we're going to use one of the points to our advantage. We know that g of negative 2 is equals to 1. So let's go ahead and plug that in. G of negative 2 is equal to 1. That is a solid point on there. And if you want to plug in other values, notice that you can, and you'll know which ones to plug in. It'll be any values less than 0. So let's plug in negative 1 as well. If you plug in negative 1, that's just positive 1 minus 3, or negative 2. And so that's going to be like right here, something like that. Here at negative 2. And so this portion of the graph, it does parabola things, right? It kind of curves upward. We call that concave up. And then let's take a look at the second portion, which is 4x minus 3. And it starts off at x equals 0. Everything greater than or equal to 0 is going to have this exact graph represents it. So it's just a line. And we do have a couple of points that we can use, like the y-intercept. When we plugged in 0, that gives us negative 3. So interestingly enough, that is going to fill the hole. So this one is a nice, perfect handoff in that a relay race analogy. And then where do we go from there? The slope is 4, so we should expect to go up 4 over 1. I plugged in kind of a larger value of 5. I don't think I want to represent that 517 on the graph just because it's like pretty high up to do that. We'd have a point like, all the way up here in no man's land or something. So let's just do the slope of 4, up 4 over 1. Maybe I should put this 0 somewhere else. I'll put the 0 right there. That's a really small 0. There we go. And if we go up 4 over 1, then we end up here. And the full line would look something like this, but we don't want the full line. We just want the line when x is greater than or equal to 0. See how we get this overlap? That's not allowed. We would cross twice on the function, so it's not allowed to draw the entire line. We're just going to go when x is greater than or equal to 0. Let's, whoop, almost got it. Wow, good thing I'm not running this relay race, or I would be tripping over my own feet. Okay, I just want to make sure that that doesn't look curvy. It should look more straight. There we go. And that is a sketch of our graph. So you don't need too many points, locations on the grid. I just want you to get the understanding of where this potential breaking point is at. Notice it's a potential breaking point. In this case, they handed off quite nicely. But in the first example, there was not a handoff. There was a split or a break. And that's going to play a huge role when we start talking about limits, which is coming up next. So stay tuned for that video. Okay, let's move on to example 3, where we have h of x. This one was a pretty easy function to look at because we just have a linear piece for the first piece, x plus 1, and we just have another flat linear piece at y equals 4, which is just a flat line. All the y values are 4, no matter what the x values are, so long as we are respecting the domain condition x is greater than 5. So let's mark that potential breaking point on the grid at 5. And here's where we're going to have a little bit of a different appearance, because we can just put 5. I'll put 5 like, I don't know, right here. Here's our potential breaking point. Here's our actual y-axis, though. Does that make sense? So I've kind of shifted the view. In fact, if you want me to go a little further out, just so that it looks a little more natural. There you go. But this x equals 5 line is really what we want to focus on, because that's where the two portions, the two pieces, are going to trade off. So let's take a look at some points here. Well, this is x plus 1 whenever x is less than or equal to 5. So anything to the left of 5, but also including 5. Well, I'm going to start off at the y-intercept. That's a pretty nice point. We also have some interesting x values here that we've plugged in. We have x equals -2 and x equals 3 and x equals 4.9. Kind of tested the boundary there, got really, really close to x equals 5. So let's plot some of those points. We have -2, -1. So 1, 2. Well, bam. There we go. And the slope of this line is just 1, right? X plus 1, the slope is just 1. So we're just going to go up 1 over 1. And then we're just going to go up 1 over 1. And then we're just going to kind of continue doing that until we get to this spot. And we're going to have a solid dot there. Why is it solid? Because we are including x equals 5. See that? It says less than or equals to 5. So we have a solid dot. And then the second piece is so easy because as long as x is greater than 5, so basically to the right of 5, the y value should just stay at 4. Let's label this a little bit more clearly. 2, 3, 4, 5, 6. That's how high up it goes. And so y equals 4 is just going to be right here. Open circle, because that piece does not include 5, and then it just goes flat. That's really all there is to it. I will make this line extend to the left, and there's not much more to do. All right, a little bit of coffee surges me through to the next values. Last one here. This one is not going to be the easiest, that's for sure. We saved the toughest one for last. We have a rational function. So you have to remember how to graph a rational function. If you're not familiar with rational functions, it's honestly going to be a decent part of calculus. So I highly recommend you getting familiar, or maybe just reminding yourself of how to work with rational functions and what they normally look like. I'll show you the parent function really quickly. F of x equals 1 over x. The general shape of this is something like that. Sometimes they call it the hyperbola function, sometimes they call it the reciprocal function or the rational function, but the general shape is this with no values allowed at x equals 0 because, of course, the denominator cannot be 0. It would cause an undefined function value. So that's just a quick recap. This is not just the parent function. This is a little bit different, but we're still going to have something really important happening at x equals where x equals 2. That's where some crazy stuff's happening. In fact, this piece exists everywhere except x equals 2. So we definitely want to point out where x equals 2 is on this grid. Let's just say there's my x equals 2. And I'm going to put this potential breaking point thing, but the funny, maybe interesting thing here is that it is literally the asymptote for 3 over x minus 2. So generally we should expect like something like that, but let's be a little bit more careful. We have some nice function values that we've plugged in. So if k of -1, if x is -1, we're going to be using this piece. We're going to be using this piece for all values except x equals 2. So when x equals -1, the y value equals -1. We got that from last time, the last video. So we can go ahead and label that when x equals -1, the y value also equals -1. And I shouldn't have tried to bend it to make it go through, because I can just move the thing a little bit. There we go. This is our y-axis. That way we can label the y-axis and get some nice points. So when x equals -1, y equals -1. Pretty straightforward. There's another component to this that I didn't mention when we were looking at the function. You might remember this from the general shape of a rational function. Rational functions have these vertical but also have these horizontal asymptotes. And if the denominator is a bigger degree than the top, then we have an asymptote at y equals 0. So in fact, our graph also has this kind of a boundary line at y equals 0. Okay, let's move on a little. What is k of 0? So what do we get at the y-axis when x equals 0? If you plug that in, you get -3/2, which means it's gone down there's -1, so maybe I should move this a little bit. I'll put the -1 here. That way I have some space for -2, and therefore have some space for -3/2, which is in between -1 and -2. See that kind of general shape that we have there? And we're going to have a similar symmetric shape on the other side. So I encourage you, plug in 3 and see what you get. It'd be kind of interesting. K of 3, we're going to use the top piece. Always use the top piece unless x equals 2. This is just 3 over 1, or 3. Okay. So then we're going to have 3, comma 1, 2, 3. There is the point. If you want more values, you're welcome to plug in as many values as you need. But this is capturing the general shape of things. Like if I want to plug in x equals 1, totally could. We could say k of 1. Remember, every single value except x equals 2 goes into the top piece. So this is 3 over -1, or -3. And you see how if I'm on the other side of this boundary, the behavior is flipped. And so we would have a point right about there at -3. Okay, that looks like it's the whole graph, right? Well, it's not. In fact, I'm going to eliminate this trade-off point. Why would I do that? Because there's going to be a value at x equals 2. It's just not going to be due to the top piece. At x equals 2, I need my y value to be -1. And so we're going to fill in that spot. It's just an isolated point. It's just a single point here at 2, -1. And this is our complete graph. Very interesting, because this thing is not continuous everywhere, but it is defined everywhere. That's very strange, isn't it? It's not connected. It clearly has some kind of breakage going on. But at the same time, there's always a y value for every single x value. So an example like this is the most interesting. All right, that shows you how to graph these things. I really encourage you to graph them on your own. Level 1 understanding is just watching passively. Level 2 engagement is at least using Desmos and opening up Desmos and trying to graph these things on Desmos. Doesn't hurt to get familiar with how Desmos works. And then, the higher level of understanding is really trying on your own to graph these things, plugging in points, not just the ones that we used, but maybe plugging in some other points, just to work on your arithmetic and to work on carefully plugging in x values and getting y values, and then also graphing. Graphing is such a dying art these days. Well, that is enough blab out of me, I think. So I hope you learned something with these 2 videos about piecewise functions. It leads us naturally into the discussion of something called a limit, but we'll save that for next time. See you then.